All right, so I'm just really going to go through kind of a series of questions that are going to hopefully prepare you for the exam, which I think is a week from today.
Tuesday.
I think it's Thursday.
Yeah, I just
pretty sure. So you have lots of time to prepare between now and then, but that also means you have lots of time to forget between now and then. For your projects, you can turn them in up until the final, pretty much, so you have time to work on them. I know several of you are now done, so good job. I will be around a lot during finals week to help. Yeah, question.
It's kind of weird. Does that have to turn in before the, because I know the finals?
No, it can be later.
So as long as it's on Thursday.
Yeah, as long as it's on Thursday, because I have to get the grading done by the next week. And anyways, basically due to technicalities, I can wait until more or less the final to give you guys as much time as you can. But we do have, I think, at least 4 people that are done with it now. So good job. I know one of you has been asking for just a data path. Annie, are you okay if I share your data path that you sent around? So, okay. So I'll post that after this class. If I don't, send me an email yelling at me for forgetting. It should be pretty easy just to plug in your control signals so that you can at least finish kind of the state machine for controlling it, even if you don't know how it works. But hers does work, so we don't have to worry about that. Exam review time. It's going to be comprehensive. It's going to cover both the early stuff and the later stuff. This isn't to torture you. It's kind of to make it so that if you were bad at the later half, you have stuff that you can get right easy. And if you're bad at the first half, then you'll do the second half stuff better. Yes. Yes, it'll be in here. If there's a crazy blizzard or something that happens again next week, I have not checked the weather and I don't trust that even if it did, then I will make remote accommodations for it because I don't want you guys to die for the sake of a final exam. And I won't want to come in either, but I don't think there's supposed to be a blizzard. Anyways, so the first thing that we're going to do on it is number conversion, right? I might give you a number like 71 and tell you guys to turn it into binary or 2's complement or hex. So if I say turn this into 4-bit binary, we do that. I'm going to make this a 4-bit binary number. No, I can't. Why? I need more bits, right? Because I need enough bits to represent this number. So if I say turn this into a 4-bit binary number, you said can't do it because it's too big to be represented. If you want, you can always draw it out, right? Your places and make sure you just double it each time. 1, 2, 4. Don't do what I do like half the time and write 6 here for some reason. I don't know why I do it, but I do all the time. That's an 8. 16, 32. Now we're starting to get, maybe we can, because the basic rule is if I can do 32, I can go up to roughly twice that, right? All of these add up to 31, and this is worth 32. So that means I can get up to 63. So I'm not quite there. I need to do 64. I could also ask the question, how many bits do I need to write this number, for example? And then we just start with the biggest bit. So this is 1, 2, 3, 4, 5, 6, 7 bits. I may also say turn this into an 8-bit binary number. So then you just keep in mind or write this down that this is what you're going to use. And you just put a 1 at the biggest thing that you can add in going from left to right. Right? So 64 plus 32 is too big, so I don't do it. 64 plus 16 is too big, so I don't do it. Still too big. This is 68. That's better. 71. Right? It's just addition. This is not supposed to be difficult. This is supposed to be 3 points. The way I write my exams, if you haven't noticed yet, is most of them are pretty easy, and then I have one or two kind of medium ones, and then one hard question. We can go the other direction. I don't think I need to do that. If I could give you a binary number, represent it as a decimal or hex, right? Just number conversion. You can use open notes, open book, open anything you want to write down, print out. You can bring a file this big. I recommend not doing that. I really do recommend making up a study sheet. Even though you can have all your notes, the process of making a study sheet helps you conceptualize what is important and what you don't know, rather than walking in with a big pile and expecting to be able to thumb through the whole thing in 2 hours, right? You want it nice and organized and prepared. The next thing that's on the list is binary addition. I'm going to make this easy on you. I'm not going to make you add 2's complement numbers here. I'm just going to make you add. Right, you can do this. No different than regular addition, although can't go to 2. So 1 plus 1 is, oh, sorry. 1 plus 1 is 2, which is 1, 0, right? I have the carry 1 plus 1 plus 1, I was ahead of myself, is 1 with the carry, right? Then we're back to 1 plus 1 is 0 with the carry. And then we're going to have 1 with a carry out. The question could be phrased as just do the addition, you write this. Or I may say, can you do this addition? Or tell me if there's overflow, simple things like that. Just so make sure that you understand adding numbers. That covers those. I could ask you questions revolving around a state machine. Right, this is highly likely. I'm going to ask you questions about state machines. In fact, I could ask you to draw me a Moore state machine. Right, how would we design a Moore state machine? So think about it for a minute. It shouldn't take more than a minute to think about how do we build. What is the block diagram for a Moore state machine? Okay, right, at the heart of the state machine is remembering where we are. So you can call this something like the state register if you would like, right? That's a good name for it. It's a register. It remembers where we are. The next component is deciding where we're going. You can just label that next state or NSD, right, for the full effect, next state decoder. And finally, we need the, this is probably square, but I'll do the output decoder, right? So we need to know what our output's going to be, where are we, and how do we get to the next place. Then you're just going to connect these together. We almost have a state machine. I'm missing one signal. What am I missing? The input, yes. Right, because my next states are going to be determined not just where I am, but also the inputs. What do I change if I want to draw an easy state machine? Yeah. A lot of times you'll see like the generic version, you'll just see kind of dashed lines. Another good question, is I could say a series of questions. Step 1, draw me a Moore state machine. Step 2, how label the bus sizes if I need 5 states in my state machine and I have 1 input and 2 outputs. Okay, if I have 5 states, what does that mean here? Not 8, right direction. So I need 5 states. How many bits do I need to represent 5 states? Yes, 3 bits. So I need 3 bits. Where does that 3-bit bus go? I'm gonna make you guys suffer. I know you guys know.
OD to next state.
OD to next state. Well, what is this wire in terms of the overall state machine or the signal? The output. How many outputs did I say there are? Two. How big is this bus? 2. Right. Did I draw this in the wrong spot? This is wrong. There we go. You guys are supposed to catch me when I make mistakes. You know this. Sorry. So here we go. This is 2. Yes, 3 bits. How many is this? Yeah, 3 bits. Right? Because I just need the number of bits required to represent my states. So remember, this is really important. If you don't remember anything else walking outside of this class, well, there's like 2 things that I'd like you to remember. But one of them is that Vhdl is not programming language, right? It's a way of describing hardware. So when you write an enumerated type that has a state, for example, right? That's that type states that we keep doing. That's just an enumerated type. It doesn't like create a signal called idle or fetch, right? What it does is create a constant called fetch that is associated with some state here. So if this was my state machine for the microprocessor that you built, this might be fetch, and fetch might be 0, 0, 0, right? Okay, so this is how we draw state machines. The next thing that we want to do that is really important is design state machines, right? Let's take it the next step further, which is what goes inside each of these blocks now that we've drawn it correctly. Okay, well, what is the state register? In this specific case, what is the state register? Yes, it's just keeping track of what the current states are. What do we build memory out of? Yeah, D flip-flops. How many D flip-flops? Yes, 3 bits to represent 5 states. Therefore, I need 3 flip-flops because I have 1 flip-flop for every bit that I have to remember. So if I'm ever remembering something, we're going to do it with some sort of flip-flop, usually D if we can get away with it, right? Because they're just the easiest to use. Let's go to the output decoder. What is the output decoder going to be made out of? Yes, combinational logic. So we design it by figuring out what should the outputs be based on the inputs and the current state, or just the current state if we're a more state machine, right? What tool do we use to do that design? What's our most powerful tool for designing combinational logic? For minimizing combinational logic? Tables. What comes after the table?
The grids.
Yes, which are called K-map.
K-map.
Yes. Yeah. So we know we're going to need to get to a K-map in order to design the minimal output logic, right? And to do it, we're going to use a table first, right? And this table, right? And the point of this, right, is to make sure that you don't lose track of the fact that we're describing hardware, because this helps you understand where your errors come from and it helps you design good code. If you don't understand that this is hardware, it's easy to make bad code, okay? So the things that we need to know is where are we, the current state, where are we going in the next state, and what are our outputs? So here,
But it's just for more, right? Because you don't have any inputs, right?
well, it depends.
On this table.
So this
Well, the
table,
one you wrote that is.
no, this depends. This can change. This table is still generic for both more and mealy. So before I move on, let's move away from this kind of generic one, right? Because the generic can be hard to translate. And let's move to some sort of useful state machine that is a little bit easier to describe. And we could say something along the lines of a sequence detector, for example. And I want to detect the sequence one, one, one. Let's switch it up. I've never done that one before. I just want to know if I get 3 ones in a row, right? If I start, and this is actually, you might build one of these someday because there are actual real problems in the world where if you have too many ones in a row or too many zeros in a row in a serial stream of data, right? Serial just means one after another. It actually causes problems. So sometimes you need to know if you have long strings to anticipate that there's a problem coming. Okay, so the state machine, first thing we do is we draw a diagram, right? Because that's easy. If I use 3 states, S0, S1, S2, this is going to be for a Mealy state machine. Okay, let's build a Mealy state machine. Why do I know it's a Mealy state machine? Just from the number of bubbles. How many bubbles would I need if I had more? 4, right? Because more takes more states. The last state, what is the purpose? That was S3. Why do I need that S3 in the case of a more state machine?
Because you have to signal that you're there, and right.
Yeah, my output.
Your output has to
specific
be
way-
dependent on the state, so you can't see your.
Yes, my output depends only on the state. So I need a whole state just to say output Z. In the case of a Mealy, I can leave this state and assert some value, right? So what we want is to start by drawing the easy path, right? 1, 1, and then I'm going to go somewhere if I see a 1. So let's say that I want to detect overlapping sequences. That's what I've always said. I'm going to have a 1 that comes out of this somewhere, right? Because this is my main path. I'm looking for a 1, 1, 1. I've actually never designed a state machine before. This is going to be really weird. Where does it go?
Those two, that's one, right? Because you've already seen a 1.
Okay. Any other thoughts?
Would it go back into itself? So it have 3 ones?
Yes, it would be back into itself. Because if I'm looking for overlapping, if we did what seems obvious, which is go back, right? That's what we've always done before. It would go 1, 1, 1 with a detection, 1 without a detection, 1 with a detection. So it'd be every other one. Whereas if we loop.
Because at S2, you already know you have 2 behind you, so as long as you're getting another one,
Exactly.
you have
Yes.
2 behind.
So this state is saying I've seen 1, 1. This is saying I've seen 2 1s, and this loop is saying I've seen 3 1s. We don't want to go back to I've seen 2 1s because I've actually seen like 5 1s, right? So then we just say, where do we go if we see zeros? In fact, in this case, it's kind of obvious, right? Because we don't have any other choice.
Yeah.
Because we're not looking for any zeros. So this one is, actually, this one is a good exam question because of the weird one here, right? But just understand that what these states represent. I've seen 1, 1, I've seen 2 1s. And in fact, in Mealy, it's the transitions. And if I wanted to be specific, what you'll see, right, is a slash nothing, no outputs, and a 1. Technically, I'm really lazy with this, and I'm not gonna lie. So if I put a variable here, this is appropriate because this says don't assert any outputs, don't assert any outputs, assert Z. If I wanted to put 1 here, then I should technically put 0 because this is saying specifically my one and only output should be 0. If I had multiple outputs, it would be like 0, 0, 0, I don't know, maybe 1, 1, 0. Right, and this tells me something different. I'm not going to do that to you, but I just want you to be aware. That's something I'll do to you in 3610. Is figure 4 conditions to decide. This is our state diagram. Okay. Then we need to turn it into a table. Right? How many bits do I need? 2 bits. Right? There's 3 states, 2 bits. I'm just going to ask you, for the sake of my sanity, and I'll put it in the exam question so you don't forget, that just binary order them and just go 0, 1, 2, 3 kind of thing. Don't do the gray code because I'd like to be similar. So it speeds up my grading, that's all. So then we say, well, if I'm in S0, right? So I've assigned my states to numbers. So I've been named S0, this is like fetch, assigned to the number 0, 0. You can always draw these tables and just start drawing it and start counting up in binary and find out how many bits you actually need, but don't confuse the number of states for the number of bits. Okay. This one is really easy, right? This is the easiest row of the table. What's this value? Don't care, and it goes all the way across. There's just a bunch of don't cares because we should never get there. Okay. Now, if I'm in state 0, let's say my input is I equals 0, I equals 1. I don't even have to put the I since there's only one input. I could just put a 0 and 1. I could say not I and I, right? There's different ways. I generally tend to do I equals 0 and then just 1 because there's this kind of implied continuity. This gets easier as you get more and more 1s and 0s. You can be thankful that I didn't teach Vem early because of my top Vems, and we could actually do huge tables and simplify them.
That's what I was going to ask. You can do as a
yeah. But I'm not going to make you do a Vem. I'm going to keep it nice and simple. I might have 3, 4, 5 states that you do, but I'm not going to do many more than that because I'm going to keep it to a 4 variable K-map. I'll just tell you that now because I don't need you to remember when you come to 3610 how to do a whole bunch of this. I need you to know, right, the basics. I want to be firm that you know the bare minimum so that when we start 3610, I can start up and we can go do cool things with it. So that's what we're testing. All right. Now we just say there's 2 different ways that you can do this. If you're struggling, I would just start by writing the state names, right? If I get a 0, we stay in S0. If I get a 1, I go to S1. If I'm in S1, right? And I'm just looking at the arrows here. Is anyone confused by this step? I just want to make sure we optimize our time here. So if I'm in state 1 and I see a 0, I go back to 0. In fact, no matter where I am, I'm going to go back to state 0 if I see a 0. If I see a 1, then I'm just going to progress through. Go to S1, go to S2, stay at S2. The output decoder on this one is trivial, right? Because it's just, we don't do anything. Right, because this is, again, I equals 0, I equals 1. Yes?
Shouldn't there be 2 ones that's in state 2?
I'm in state 2 and I saw a 1.
If you made it a more and added to the state 3 and state 3 was what was when you found it, they would both be 1, even if you found 0, right? Because 0, you're going back 1, you're going back to itself, but either way, that final state is I've got it, so it's 1.
Yes, yeah. So that's the thing. If it's a more, it doesn't depend on the inputs.
It would be only 1. There would be any. It would be.
Well, yes, yes. Let me get there. So if there's no inputs, if it's a more state machine, there's 1 column, right? It only depends on what row we're in because each row corresponds to the current state. Easy peasy. Okay. That's why I'm doing the melee is actually the harder of the 2 situations. So if you get a more state machine, it's just easier. Okay. This is still trivial, right? Because this is don't care, don't care. We know we could simply write it as, if we didn't worry about simplification, this output is, well, we got to call this something, right? And we could call it C, we could call it Q, because if we think about it, this is a Q, right? Our current state is the output of a D flip-flop. So this would be Q0, Q1 is probably a really good name for it. which makes these D0, D1, right? Because those are the inputs. And that just corresponds to the diagram that we drew earlier. So Q0, Q1, the obvious answer is not Q0 and Q1, it's just an AND gate, but it's actually simpler than that because of these don't cares, right, that result from this state. So we can see that it is really just if Q1. You can of course draw a K-map of this, which we'll do for the next state decoder. But if you're asked for that, it can be really simple and straightforward. Okay. Next step, we need to just start assigning bits, right? The D0, D1 bits. State 1 is 0, 1, 1, 0, 1, 0. Now I have my D's and Q's associated. So I have now binary so that I can actually do a K-map, right? It's hard to do a K-map with an S2. Doesn't mean anything for us. Now we draw a K-map. I don't think we need 4 variables, right? I think I only need 3, but I just drew a 4 variable K-map. Because what variables do we need to decide? And this is just deciding what my next state bit is, right? We're looking at where am I, which means inputs, to where am I going. So where is D0 going? Where's my lower order bit of my next state? And that depends on my current state, which I'm going to say is S0, sorry, not S0, Q0, Q1.
I have a question real quick.
Yeah.
When we were talking about the output, you said the output was only Q1, right?
Yeah.
Isn't it Q1 and I equals 1 because it's a.
Oh, yes, it's probably Q1
because it's
and
immediately, so
I
you have
is
to check
1.
that I equals 1.
Yes.
Or you're getting an output every time you hit S2, so that would only be a 2. Like it would only.
Yes, you're correct. Yep, yeah. You could draw the K-map just like this, right? We'll take the Q's, Q0, Q1. The other input that I decide on is I, right? And that comes from this next state diagram block, and S, and I, right? This is my I. These are my 2 state bits. Now that I've chosen this, what I like to do is go, well, I don't need 4, so I'm going to cross these off. They're not helpful. Then I just recognize, right? Remember this, your K-maps need to be gray coded. Don't forget that. It's been a long time, but don't forget. Because there's got to be K-maps on this exam here, maybe just doing them. But I think doing them here is a good review. So, because this is the hardest use of the K-map, right? This is a real applied actual use K-map. And then we just say, well, if I'm in 0, 0, and I is 0 or 1, then where am I going? Keeping in mind those red underlines are my D0s, right? So that's what I'm looking at. So if I'm in 0 and I see a 0, I get a 0. If I'm in 0, I see a 1, I get a 1. Okay, this is my state, 0, 0, 0, 1, 1, 1, 1, 0. That's 0, that's 1, that's 2, don't care. Right? So we can see ahead, we know this is going to be don't cares. Because this is saying I'm in state 3 and I don't care. Now I know that I can just go top to bottom following this. So I'm in 0, 1, I get a 0 is 0. I'm in 0, 1, I see a 1, I get a 0. I'm in 1, 0, I see a 0, I get a 0. I'm in 1, 0, I see a 1, I get a 0. Oh, this is trivial K-map, isn't it? You can see now that this is probably not the best K-map. In fact, I could ask this question. If you ended up here, and I could ask the question, why isn't this state code assignment the optimal state code assignment? Why is this a bad one? Yeah.
Wouldn't you want the one next to one of the don't cares?
Yes, yes. So if I gray coded this and had flipped S2 and S1 state code assignments, then I would end up with don't cares over here. And then I could do a 2 circle. As it stands, the only thing that I can circle is this one. Do I need to circle the don't cares? No, because it's optional to circle don't cares. Don't circle them if you don't need them, right? Because it adds complexity, but we'll do another K-map example shortly. So what this ends up with is 0, 0, 1, right? So the D0 equation is not Q0, not Q1, I. Right? That means for D0, if we were to put this on a breadboard, I would need a 3-input AND gate. Okay. D1 is the same thing. I just use a different column of my bits. Right? It's 0, 0, 0, 1, X, X, 0, 1. That's my K-map. I do the circles. I get my results. I could then ask you to draw. Oh, for the video people, that was probably bad, but so here's my I. There's the 2 bits of my next state decoder. These are my 2-bit output. After we do both the D0 and the D1 equations, I could ask you to draw the circuit that is my next state decoder. Now, we didn't do this, right, in Vhdl. We didn't do the logic for this because it takes care of it for us when we write the next state should be whatever, right? But be aware that this is what is happening. Because when we get to 3610, I'm going to talk about some additional issues that can arise from how you choose your variables. So that's why I want you to know this, is because it comes in relevant when you start talking about like high-speed design and such. This book mentions it a little bit, but I didn't go too deep there. Okay, so if you want, you can go build your D1 on your own time, practice it, build it. I'm not going to take the review time to do so because I want to use the review time to do more complicated K-maps, because you're going to get some K-maps, right? This is testing to make sure that you know how to use a K-map at all. Sorry, I shouldn't say at all. I should make sure you know how to use a K-map in a real design. If we wanted to go further and just make a more sophisticated K-map, this is one way of doing it, right? The order in which you assign these matters a lot. This ordering I just find useful for the state table assignments, because if I had a 3rd state bit, right, if I needed 5 states, then I need 3 bits. So then I would need to put a Q3 somewhere, or sorry, Q2. And that would be a 4-variable K-map. And this one, you have to ask yourself, because you'd have 0, 0, 0, 1, 1, 0, or 1, 1, 1, 0 here. And so this means each row of the column is toggling Q2. And I'm not sure I like that. I think maybe I would swap those 2, right? But if you want, you can go invent yourself a 4, right? This is really easy. These sequence detectors are really easy to practice because you can just go, I want to detect 1, 1, 1, 1, 0. Well, go draw that state machine, build a table, design the circuits. You've done your practice, right? and you want to shoot me emails with pictures of your work, and did I do this correctly? I can check in 5 minutes or less, hopefully less. If it takes me 5 minutes, it would be that bad. Okay, K-map. Let's make more complicated K-map. Take a minute. And the question here is something along the lines of design, or I could say draw the minimum logic for this K-map. Right, and the first step is write the equation. We really don't go that far, so let's write the equation. The minimized expression for this K-map. And generally, I will specify sum of product or product of sums. If I don't, you can choose.
To wrote BA, is it, are you entering it like BA, like B not A, A not,
Yeah.
BA not, okay.
0, 0, 0, 1, 1, 1, 0. So this
It's not an alphabet.
is not a. Yeah, it corresponds to the order of this that they just stuck across. All right, you guys keep working away. I'm just gonna get these drawn up. Right, this is one circle. What is the vocabulary word for the circle? I know, gotta dig deep, it's been a long time. Grouping. Starts with an I. Implicant. What is an individual square in the K-map? What's the vocabulary? Go look it up. I can tell you. Right, simple vocabulary words. You want to make sure you understand what I'm asking when I ask questions. So the next one, we got to take care of these two ones. Don't be tempted to circle them on their own, because if we can make a bigger circle, larger implicant, we want it because it means there's fewer terms in that part of the expression, right? That's the best we can do, right? Because we can't do threes, we can't do diagonals, it has to be squares or cubes. So this means if I'm writing a sum of products, right? Which means that if I call this Z equals, and then I have one product term for each implicant, right? So this one, we write what doesn't change. So what doesn't change here is 0 to 0, so A doesn't change. And because it's a 0, it's not A. When you write these on the exam, alphabetize each product term. Then the other thing that doesn't change is the top to bottom, 0, that 0, right? Because the C changes, the D doesn't. So it's A, D, the D is 0, it's not D, or, right? That's my first product term. This is my smallest one because it's my largest implicant. This one's pretty easy because we see that A doesn't change and B doesn't change, and they're both 1, so it's A and B, but we also have one more because of this direction, right? It turns out it's the D that doesn't change, ABD. Or next product term, left with this one, well, then the AB column, it's just A that doesn't change. And here, it's both the C and D, and they're both true. The expression is done. Any questions that far?
And products of sum would just be switching the ones.
We'll do the product of some though, same map actually. I will do that. But yeah. Can we draw the circuit? You guys draw this circuit? Right. This is 1, 2, 3 AND gates. Into a 3-input OR gate. Right, and this is just A bar, B bar, and so on. Now, the next part of this question, if I ask you to convert this to NAND only logic, how do we do that? Bubble pushing, right? Again, it's going to be easy. Bubble, 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 bubble. Done. I build a NAND only circuit using a K-map. If I then ask you the question like I did on the first exam, if instead I had wanted to design a NOR only circuit, what would I do differently? Well, you can push the bubbles through and do weird things, or you can go the easy way and just do a product of sum expression instead, right? That's the easiest way to design a NOR logic is using product of sums. In which case we circled the zeros. We're really only left with this pair that is kind of annoying. If this one was a 0, it'd be good. If this one was a 0, we'd have another cube, right? But we're stuck. Once again, it's 3 different, in this case, it's not product terms, right? This is now sum terms because it's product of sums. So the second word, the sums, is the thing that starts. So what we do is we again look at what doesn't change. Well, the ones don't change on here, which is the A. And so we say, okay, well, A doesn't change and D doesn't change. Right, because now it's a product of sums multiplying a bunch of additions. What's wrong with this? What haven't I done yet? The bar, where does the bar go? Yep. BA. Right, because in the case of the product of sums, it likes to be confusing and we're looking for zeros, so ones are false, right? This is active low logic. That's what's different. That's why we do these circles. If we wanted to convert from here to here, what is the mathematical theorem that we use? The Morgan's theorem. No surprise, I'm probably going to give you De Morgan's question on there somewhere, right? I know I mean something else. This circle, D doesn't change, and wrapping around, A doesn't change. A's are 0. Is that right? D doesn't change and is a 1, so it gets the bar. A doesn't change, it's a 0, so it doesn't get the bar. Last one, this is going to have how many in it, right? It's going to be 3, yes, exactly. And so this is the easy one to start with because we're going to know C or D, but I want it alphabetized, so let's deal with the A first. A or B. It's the B that doesn't change. No bar because B is 0. It's a 0 that doesn't change. In this row, it's C, D. And there's 1, 1, which is the D, so the D gets the bar. There could be a question that I could give you something with like lots of zeros, only a couple of ones, and I might ask a question such as, using your choice of sum or products, design the minimum logic, right? Because one of these is actually simpler than the other. In this case, it's a minor difference, right? Because this one has two input OR gates and one 3 input OR gate, where this is 2 3 inputs. So that one is actually simpler. So you have to make informed decisions. Normally it's driven by whatever technology we have at the bench or, whatever, not really by what is more minimal, but.
This is still an abstraction over transistors. So if you want to really talk about minimum logic, you want to see it.
Yes, yeah, we could do this even better with transistor level design. That's K-maps. I think we're okay if I don't do any more, yeah. All right, making these up is actually really hard. So if I gave you this circuit, I know what question I'm going to ask for this circuit. If I were to ask the question, which of these inputs has a static hazard on it? This is digging real back hard. Do I have one of these on exam too? Let me double check exam 2, because if I didn't give that, I might not have to give you one of those. Did I not teach static hazards? Did I let that one slip? Okay, never mind. You won't get a static hazard. Oh, it's B.
Because it goes through 2 gates and 1 gate.
Yeah, so gates are not ideal. They take an amount of time for things to propagate through them. Maybe I'll give you, if I end up with time, I doubt it, but if I end up time in this room, I'll explain it because it's useful to know. It wasn't high on my priority because we actually start out there in 3610. And so it gets confusing to me when I'm teaching multiple sections of related courses, so that's probably why I missed it. But basically the idea is they're not ideal gates, right? So what's going to happen is it's going to take some amount of time if B changes for the output, say F, to change. And in one path, it takes longer than the other path. And so there's what's called a static hazard, which is if the B is what's making it true on one path, but it's not true on the other, then we can have a problem when it's supposed to change. B goes from 0 to 1 and it stays true, or the output should. But because the two paths are different lengths, it can dip to 0 for a little bit of time before the signal propagates all the way through. So that means in this case, what I'm going to ask, I'm still going to give you a circuit. I'm going to ask a question along the lines of, write me an expression for F. I'm really sad I didn't give you guys static hazards. They're kind of fun. Okay, so the way that we do this, right? The nice, clean, straightforward way is by doing each of the intermediate signals. Don't skip to the end. So here is just B or C. Oh my goodness, I didn't even connect one of these, did I? Oh, here we go. Let's make that connection.
The one input XOR.
One input, yeah, exclusively or with a, yeah, that makes no sense. It would actually, that implies it's always 0. But, anyways, so now here, don't forget, this is A XOR B. That's the easy way to draw that, right? This one is A and not B. And that just leaves F. Because I have 3 inputs to F, I can forget about everything before there. And I just write these. Right, it's B or C or A XOR B or A not B. I can then ask you to simplify this expression. I may specify K-map or Boolean algebra, right? So we would have to look for things and ask ourselves, is this the minimum expression? It turns out that XORs are really hard to simplify, right? So generally, if I'm going to make you do Boolean algebra, I'm probably not going to give you an XOR gate in it, just to not torture you. I don't even know if this does simplify, actually. Anyways. I am likely to do something like exam 2, where I give you some code, some VHDL, and ask you, what is this code doing, right? And it could be AND gates, OR gates, full adders, so on. I could ask you really simple questions like, using only 2 input AND gates, write me VHDL for a 4 input AND gate, right? Or I might give you, here's an entity for a 2 input AND gate. You declare signals and make the connections to make a 4 input AND gate. Why not? Let's do it. So I can say, you have access to this entity. Go ahead and design using this and any signals that you need to create to make a 4 input AND gate. Okay, so I'm not going to be super specific, right? If I'm asking you to handwrite the code, it doesn't need to be exact, but and you can use shortcuts like SLV is standard logic vector. That's not right, is it? Shouldn't be a vector. All done. So what you would do is you would just kind of sketch out, and I would probably give you the rough structure of this to do it. I wouldn't make you kind of go from absolute scratch, but there's going to be, you would have to have some entity. We're going to do this actually as so you write that, right? Now we have an entity. This is the top level. This is what a 4 input AND gate looks like. Has 4 inputs, 1 output, 4 input AND gate. Now we have to build it. So we're going to, somewhere down here, we're going to have an architecture. And inside of that architecture, I'm going to need to do something. But before I do the stuff in the architecture, what do I have to do? Yes, I have to declare the component, which is, I have to say, well, I'm not gonna draw it out. You're running out of time on your exam and I have something like this. This will give you some points, I won't give you all the points, but be like, okay, I'm running out of time. I know I have to declare the component there. Yeah. Is it? What comes after the architecture in this case? Yeah, well, the signal declarations go up here. Right? What goes in the architect? Right, anytime we make something exist, it goes.
But it's after when it says like.
Oh, I see what you're saying because I'm done. Yep.
And then the begin back.
Thank you, Annie. You're smart. No, this is fine. I actually like that I made that mistake because it means you're paying attention and it means you understand, which is really good. So make signals exist, make component exist. What comes after the begin? Do I need a process? No, I don't, because it's just combinational. It doesn't even remember anything. But I need to use these components, right? I pulled the bin out of the closet and now I have access to them. I need now to pull them out of the bin. And so I'm gonna have like and 0 and 1. And this is just the name for the components, right? And 0 being something along the lines of, well, I need to make this part exist. What is it? It's an and 2. It has a port map. And that port map is going to have these A, B, and C. In fact, both of those are going to have the same thing. Take just a moment to finish this. Make sure that you can do it on the solve the answer. So the A and B, the inputs are kind of the most obvious, right? I'll switch colors so it's clear what I'm changing. P, Q, R, S, right? In case you're confused. This is what I'm building. What am I missing? Yep, another AND gate. This is why it's important to be able to write a picture, turn it to code, because you recognize missing an AND gate. And that needs an A, B, and C. Okay, let's do the hard part. This is the hardest part of this whole design, right? Where does the C go? To a signal, right? I don't have that signal, let's go make it. I I've used ABC, PQRS, XYZ. Really, I only need two internal signals, right? So X, Y, sounds good. Make sure they're different, don't want to overlap. So if I put an X here, that means I've made this X. Where does the other end go? Into A of the AND. Now I've connected the output port of this AND gate to the input port of this AND gate, right? Keeping in mind that right here is AND 0, AND 1, and 2, right? That's what they are. It's an AND gate called AND 1 with a signal called X connecting AND 0 to AND 2 and a signal, well, by implication called Y. It goes where?
Wait, so sorry.
This Y, which is this Y, where does it go? Yes, it goes to B. There, right? That finishes that connection. I named a signal, meaning I pulled something out of a box and plugged it into two ports. If I don't plug it into ports, it's flying in space and nothing happens, right? If I don't connect something, it just shouldn't exist if it's not connected to something on both ends. Finally, what's the C? F. Yes.
So I have to make a signal for F.
No, I don't, because it is a top level port, which anytime I have a top level port declaration, it creates a signal affiliated with it. Yes. Yes, because what's happening is I have a box drawn around this, right? And this black box is AND4. That's this entity. It has this port called F. On the inside, this signal is called F. But the outside world doesn't know that F is a signal. It doesn't really know anything about F, other than there is a port called F with a standard logic type. So now if I wanted to build like a bigger gate, right, I could use this 4 input AND gate to build, I could use 3 of these to make an 8 input AND gate. Or, you know, start scaling it up. So I would need a new signal on the outside. So internally it's called F. Externally it's whatever I call it. Just like in the case of the AND gate, externally this is called X. But on the inside, it's called C. So that what this is saying is, on the inside, I have something called C. And I want to connect it to the outside world using X. So the inside A is going outside to P. Inside C is going to the outside X. Inside A is going to the outside X. So I have inside here a signal called A that is connected to X, which is connected to port C, and inside is called C, right? And that's where the biggest confusion of Vhdl comes from, is this transitioning from the outside world. And we have to think of things hierarchically, because otherwise we get confused in what's going on. Yeah.
Should there be a third entity for the gate?
That's this red line here.
Yeah, we need like up top, like with the ports.
No, I don't, because I only need to declare the AND4 entity, which is this big black box, because this is what I've asked you to build. Yeah, and then I've made a component using the AND2. And then I'm just using 3 different and2s to build my and4. Yes.
So I don't know, yes, you have two entities in the same block.
No, this is what I would give you in the
Oh.
assignment statement. So I'm saying that I'm providing you an entity with an and2. Build me an and4 using it. Yeah, that's the question.
I was just confused because I thought.
Yeah, sorry. Yeah, the problems of whiteboard drawings. I apparently say more often the longer the semester goes. All right. The next most important thing that we need to cover is timing diagrams, right? Because they're really important. You've gotten much more comfortable with them, I hope, over the last couple of weeks as we've been using Vhdl, which shows why they're so important. So we can do something. Last time I gave you on exam 2, I think I gave you a combinational timing diagram. I can just as easily give you a sequential timing diagram. Finish the timing diagram. If I don't give you a starting point, you can generally just choose one, but the more correct right is I don't know. I will have to specify rising or falling edge, or I'll give you a picture of device, right? So if I give you this device, or specifically, what's the difference between these 2 devices? Yes, rising edge triggered, falling edge triggered. So let's use this one, rising edge triggered one. Step 1. Mark out your interesting points. Anyone see a potential problem with this design at the moment, the sine waveform? Exactly. So what vocabulary words do we have associated with that we might use to describe the problem? There's like 4 different valid words. Not quite. The delay time is a timing associated term. Yes. We've violated T setup and T hold. We've also created what's called a race condition, right? Because we don't know if this rising edge is going to happen before or after this falling edge, right? So that's what I'm going to be looking for. I can be specific. I could say things like, these are ideal devices. Generally assume that they aren't, unless I say, I might also be more specific and be like, your setup and hold times are 1/4 of the clock period. And then you have to ask yourself, okay, is there any other violations? Well, no, because every other time I've changed more than 1/4-ish, except for maybe here, right? This is potentially an issue because a clock period is here to here. So half of that's here, 1/4 of that's here. That's really close. So I would probably instead say like an 1/8, and then it's clear that this is not in violation, except for here is clearly a violation. So what happens? Well, at each rising edge, something interesting happens. So the answer I'm going to do in red We don't know until a rising edge happens. And I could specify another timing term, which is the clock to Q delay. And I could say that the clock to Q delay is half a clock period. Let's say it's a really slow device compared to the speed of my clock. So it comes in, the clock happens. I still don't know until here, and it becomes a 0. Right? Because it takes half a clock period by what I just said to go from the D to the Q input after the rising edge. That's what clock to Q delay is how long this delay takes. As I recommended before, anytime you're doing timing diagrams with clock devices, draw it with a little bit of delay regardless, because it just makes more sense if you string 2 of them together, right? Because they're more likely. This is actually a really good exam question. Draw this timing diagram. In fact, you may want to use this for practice because I'm not going to have time, I don't think, to do all of it, but we'll see. So there's another rising edge, but it can't change till halfway through. It sees a 1, so it goes high. It can't seize another rising edge, can't change till here because of the clock to Q delay. But what happens at this point? So what happens here?
It goes low.
Why would it go low? Because the point is we don't know if it's a 1 or a 0, right? We have that timing violation. We don't know. Right? That's what happens with the timing violations, is we don't know what happens. Undefined. And it must stay undefined until here because this rising edge does clock the 0. But we don't know what happened in between.
Why doesn't Q go higher? That's like
Here?
Yeah.
It does, but here, because there's a half clock period clock to Q delay that I said.
Oh,
So this rising edge takes half a clock period to implement.
so in a question, you could state that it's like there's a half.
Yeah, I would say the setup time is an 1/8 of a clock period. The whole time is an 1/8 clock period. The clock to Q delay is half a clock period. Draw. Draw Q1. Excuse me.
So that second unknown, is that also because of the half clock delay?
No, well, yeah, it starts here because of the half clock delay, but it is unknown because of the timing violation. Sorry, apparently I've been talking too much and my voice is done. It's been a very talkative week and I guess that's it for my voice. That is actually the bulk of the exam we've already covered. There will be a question about the project where I will give you a series of memory. I will write out the memory like I have a dozen times on the board. And I will ask you a question about it. And it could be, what is the result of this memory? What is the output of, what would the output of your microprocessor be at the end of this program? Or it could be, write me a program to multiply by 4, right? That would be like the hardest thing that I could ask, because it would be actually really hard because you'd have to like add and add and add and add. I won't do that, I promise. I'm not going to multiply, but I could ask you to do, I could ask you to add a couple of numbers together and store it in a specific memory location, right? So you need to understand what your microprocessor is doing so that when I give you a memory, you can go, okay, I know what this is. So if you don't take the hint, print out your projects, right? You want your projects at hand, at least the project description, so you know what the opcodes are. Most of you could probably do it without, just because you've seen the op LDI and op FC so many times, you kind of know what they do. But that could be a question. And I will also give you another scavenger hunt style VHDL code, right? But this time it's going to be sequential memory instead of just combinational. And it's going to ask you to find the errors. And at least one of those errors is going to be functional, meaning like something is connected wrong. It goes to the wrong state, something along those lines, okay? I have good news on the state machine process that I have you do. I've actually found a way to decouple entirely, to draw the state diagram, draw the table, and then solve the logic. So if you make an error in any one, it's not going to cascade through. So I've solved that because I hate grading it, actually, is the whole reason I didn't do it for you. I did it for me. Timing diagrams, code errors. Other than that, I mean, studying exam 1 and exam 2 is going to be really good because I'm going to base a lot of questions on those, understand state machines, understand your project, and you're pretty much good to go. I don't think there's going to be any big surprises here. I think I've told you more or less everything that's going to be on it. If you end up wanting to hang around for a minute or two, I'll actually finish solving this. If you need to go, you're free to go. Okay. So now what we have to do is anytime that we have a diagram, it's best to do what I've already done, which is solve an intermediate signal, right? And now that I'm done with Q, I can forget about the rest of that. I just have to focus on the clock and Q naught. And what I want to do is recognize that Q1 cares about the falling edge. And it's going to have the same device properties, let's say. Let's say it also has the 1/8 setup time and the half a clock period clock to Q delay. Well, this is interesting because I don't know until the first falling edge. And this first falling edge, there's a bit of a problem, isn't there? What's the problem? Yeah, I still have that race condition. I'm not going to meet because it's unknown right up until that line. And so what is it? We don't know still. So at falling edge, well, this don't care or don't know is still left over from here. And we're going to not know until here, right? Halfway through the next one. Well, and then the question is, do we know? Well, guess what? We don't. Because it just changed. Whoa. So we still don't know. Here, we've clocked a new one in. We don't know. I've clocked another one in. I don't know. I don't know. Right? That's the problem with these timing violations, is there is always something else that depends on your design. And so when you break it a little bit here, you've broke it completely down the line. So now you have a random number generator. Ooh. Except for not really, it's not even that good because what happens is that it's predictable. So it's a pseudo random number generator with a high degree of predictability. So it's not even good for security purposes.
Why don't you see anything on the very last one?
Because this don't care is still up until this point is don't care or don't know. And so it still violates setup time.
But at the next falling edge, you have a 0, right?
Well, at this falling edge, I have a 0 afterwards, so I meet hold time.
Oh, but it's going up to it.
But I've broken setup time. So if I don't meet setup and hold, I don't know the result. Because what's really happening from a device standpoint is each of these rising edge of the clocks jump about a little bit. They're not perfect. They wiggle back and forth. And so that's what the setup and hold time, or at least part of what the setup and hold times are designed to fix, is let's allow for clock jitter. Let's let that clock bounce back and forth without causing us issues. And that's one of the things that really limits our ability to go faster in a clock is clock jitter, bounces back and forth. So we have really advanced classes, well, we don't hear yet, but we will someday, that talk about designing clocks so that they have minimal jitter. The other issue, right, is that it's not perfect. It does this as well. And if you remember way back to like lab 3, where we built a comparator, and remember how the comparator isn't precise. It has hysteresis, which means directionality matters. And so the question is, at not only what point in time does this start to change, at what point in time, once it has started changing, does the comparator flip over and decide that there has been a rising edge? So you have tons of unknown issues around setup and hold. But for freshman level, all you have to understand is you need to meet these timing requirements of setup and hold. You don't have to understand why yet. Yeah. Okay. I just wanted to finish that so you could see how crazy things get and have that example. Expect timing waveform on there of flip-flops. It will be sequential. Maybe also combinational. There might be 2, right? If I want to be fun. There's not just the flip-flops, right? We have like SR and JK and all the other ones. I will try my best before Tuesday will be my target. I will try and get out some sort of practice exam, something that you can run through and hopefully have some extra questions. I'm about done writing the actual exam, and then I'll build the practice kind of inspired by that. You're welcome.
So the difference between a sequential and a combinational timing diagram is that combinational, everything happens at the same time.
Everything happens as soon as stuff happens.
The main difference is there's no clock. There's no if rising edge
Oh,
statements.
sure. Okay.
Yeah. So basically, you would just draw those lines down for every interesting point that one thing changes from one to another. Yep.